In this assembly exercise, we're going to model what we call a unit cell of a crystal structure. So metals have crystal structures like this, where the atoms are arranged at regular intervals, tightly packed together. So what we're going to model is called the simple cubic. So we have a layer of atoms which are modeled as spheres, and they're touching each other, and then above that we have a second layer, and those are directly above the first layer. So again, we call this a simple cubic because the atoms are, if we looked at the centers of these and linked those together, they would form a cube. So what we'd like to determine is what we call the packing factor, that is, of the available volume, how much of it is taken up by atoms and how much of it is the space around the atoms. So making this assembly might be kind of difficult if we were to use our regular tangent mates, because it takes a lot of them to completely get these things where we want them. So we're going to use a little different approach. We're going to use a 3D sketch to actually locate where those atoms are going to go. So before we do that, I want to go ahead and look at the atom model, which again is just a sphere. But if you haven't made a sphere before, you might find it's a little more challenging than you thought. When you make the sketch, you can't take an entire circle and revolve it around a center line. It doesn't. SolidWorks does not allow you to do that. So what you have to do is draw a circle, then cut it in half from the quadrant point to the quadrant point with this line, trim away half of the circle, add a center line, and then you can revolve this around the center line to make the sphere. Now I've used a radius of 1. I'm working in inches here, so that would be like 1 atomic unit would be the radius of the atom. So I'm going to open up a new assembly, and I'm not going to put a part in right away, so I'm going to go ahead and hit the X there, and I'm going to start by drawing a 3D sketch. And when I pick the line tool, I can sketch in any of the three primary planes, but let's start out with the XY plane. And as I draw these lines, I want to make sure that they're along the y-axis, along the x-axis, parallel to the y-axis again, and then this last line I'll just have to connect back to the first, so I'll have to add that along x relation manually to that. So I'll pick this line and add the along x relation. We could also turn on the sketch relation so we can see along y, along x, along x, along y. Now let's put a dimension on this. We want this to be 2 inches because we want the two atoms that we're going to place on the corners to just touch each other. And let's go ahead and take 2 of these edges, one horizontal and one vertical, and add an equal relation to those so we're fully defined. And let's keep going. Pick the line again. This time hit the tab key and switch over to the YZ plane, and so we'll come out along the z-axis, down along y, and then back to our original point. Okay, pick this bottom line since that did not get an automatic relation, and we'll put that along z. And now if we take this line and with the control key hold down this line and make these two equal, then we're back to being fully defined. Okay, and we'll keep going. Again, in the YZ plane is fine. We come along the z, along the y, and back to the beginning, and add our along z relation here, and an equal relation between these two lines. That's really all we need, because we now have all corners of the cube identified. But let's go ahead and just add these lines, and it doesn't matter what plane we're in now, because when we go from a line to a line, from a point to a point, the line will automatically snap to those points. So we have a sketch here. It's a cube, and we're fully defined. So let's go ahead and close that sketch, and now we'll start bringing in our components. Now, of course, the atom is what we want. The first one, I can go ahead and just hit the check mark, and it will snap to this point right here, which is where the origin was. Let's go ahead and add a total of 7 more. So if I hit the push pin here, it allows me to put in multiples, and so now I have a total of 8 atoms here. Now, to add the mates, what I'm going to do is display the origins of all of these parts, and now I can simply go and pick a corner point of the sketch and then the center of one of the atoms, and just keep doing that. And again, you'll find this is a lot easier than adding all the tangent mates that would be required. So a lot of times sketch is a really good way to lay out things within an assembly. And finally, one more. Okay, and we're done. So what I want to do now is hide the sketch, and we can also turn off the display of the origins. Now, as I said, we want to calculate the packing factor here. So to do that, we need to cut away the pieces of the atom that are outside of our cube. So, and you'll see that a little better, I think, once we do that. Let's go to the front plane I want to sketch in, so we'll go normal to it. And I want to pick a corner rectangle, and I want to go from the center of this atom down to the center, if I can find it here, there we go, center of that atom. Then I want a second rectangle completely around our entire assembly. Let's go to the assembly tools and pick from assembly features an extruded cut. And so we want our type to be through all, but since we're part way into the assembly, we need to go in the other direction as well. So we click direction 2, make it through all as well, and hit the check mark. Alright, now let's sketch on this top surface, and once again we use a corner rectangle to link these two centers, and a second rectangle around the entire assembly. And in this case, when we pick the extruded cut, we only have to go down in one direction, but still through all. And this is our unit cell. So this becomes the basic building block. I can stack these on both sides, well, on all sides, above, etc., and make this a repeated unit. So to determine the packing factor, we know that this is a 2-inch cube, so it has an available volume of 8 cubic inches. Now if I go to the mass properties, I can see the amount of solid material I have in here, that is the amount that's due to the atoms, is 4.19 cubic inches. So with that in mind, we can calculate our packing factor by taking the 4.19 cubic inches and dividing it by the available 8 cubic inches, and this becomes 0.52, or 52%. So not a particularly efficient way to pack the atoms in. About half of the available space is just taken up by empty space here, and in fact this isn't a structure that's seen in many metals. What's much more common would be, let's open up here the body-centered cubic model. If we just push these atoms far enough out on the corner so that we can put one in the middle, and we can also cut pieces away to show the unit cell, it turns out that this arrangement has a packing factor of 68%, and iron has this structure. Some other metals, such as aluminum, have a structure that's called the face-centered cubic. So in this case, you can see that there's, out of this face of 5, you can see there's one right in the middle. Now all these, and let's go ahead and look at its unit cell. And this has a packing factor of 74%, so much more efficient at using the available space. Now in all these cases, the sketch is not that much different. We can just take our original cube, and in this case we've added a diagonal across each face and put a point in the middle because there's going to be an atom attached to each point. And of course the dimension now goes across one of these diagonals, because if we have an atom here in the middle, one on each of the corners, it's going to be a total of 4 units from corner to corner. There's also another one that's a little bit harder to do, and that's the hexagonal close pack. And I've shown it here, and it's in an exploded view. So if I collapse that back down, and when we show the unit cell for it, you can see it's a little bit more complicated, but it's not that much different than the face-centered cubic actually, and it turns out to have the same packing factor, 74%, as the face-centered cubic. So in materials class, you'll learn how these structures can impact the mechanical properties of the metals.